Next up, we have Dallin Durfee to speak about slow ion interferometry and searches for possible photon mass as a result.
All right, thank you very much. I have to admit it's a little bit intimidating being in front of this crowd, but I'm really excited to be here, and I'd like to thank the people who organized this and who invited me. So, as it says here, I'm working on slow ion interferometry. So I probably don't need to give much of an introduction to this field because most of you, I think, know quite a bit about this. Charged particle interferometry has been going on for a long time, as you may have noticed from some of our previous talks. Alex gave some great reasons why physical gratings are a neat new way to do electron interferometry. But what we want to do is we want to do something a little different. We want to make an ion interferometer. Ion interferometers are not unheard of. Hasselbeck has made one, and that's been very helpful because now we have something we can look at and compare what we're doing with and kind of get a better feel for the experimental parameters that will make things work. He did his experiment using biprisms, similar to a lot of electron interferometer experiments, and that has a great advantage, which is you don't have to mess around with lasers. And we all know about lasers, right? Okay. But, however, one of the unique things about ions that makes them really exciting is that they do interact with light, and so it opens up the possibility for a charged particle interferometer where you can take advantage of laser cooling, so you can control the velocity of your ions very precisely. You can use optical rather than physical gratings. That's going to keep your ions far away from any physical surfaces and reduce systematics. Yeah, Alex also gave us a great introduction of the interaction of charged particles with gratings. And as you saw, it was a very complex and rich system to study, one that we don't want to study. We want to be able to move on to other things. So the optical gratings will help that out. Also, in the experiment we're going to be doing, we're going to take advantage of state selective readout. So rather than actually having to image individual fringes, we'll be able to get the phase of the interferometer by measuring the state that the atom comes out of the interferometer. All right, now, so you can see there's some interesting things, some interesting reasons to want to make a cold ion interferometer. But the real motivation for this experiment, of course, is that Dave Pritchard said that this will never work, right? So we have to, is Dave here? Oh, he missed it. He can't defend himself. No. Dave Pritchard never said anything about this. I just wanted to throw that in. Okay. All right. So our charged particle interferometer, basically if you have a charged particle interferometer, what you've got is a very sensitive field detector, and you can use that to do all kinds of interesting experiments. For example, one thing that we're really interested in is studying material properties. Using a transmission electron microscope, for example, you can look inside materials. With this, you'd really be looking at the surface fields, the fields just outside of the material. In particular, we have someone in our department who works with colossal magnetoresistors that are actually used in hard drive read-write heads. So make a tie-in there. These colossal magnetoresistors, the way that he studies them is they do calculations, they look at bulk properties, they look at electron diffraction. But really, of course, you care most about what's happening at the surface. So you might imagine I make an interferometer, and I can bring a piece of this material close to one of the arms of the interferometer, move it back and forth, and I have a very sensitive way to measure the fringing fields just outside of the surface. You might also imagine throwing some dilute gas in the experiment and measuring the collisions between the ions and neutral atoms very sensitively. But the thing I want to focus on here is kind of this is the experiment that we hope to get to, which is going to be kind of our big thing that motivates us, and that is tests of Coulomb's law that you could do with a charged particle interferometer. All right, so the thing that got us thinking about this was I had an undergraduate who was taking a practice GRE exam, and it had a question about how do you know that the Coulomb's inverse square law is right. And so he went and looked into this, and of course, Coulomb's inverse square law has been tested many times. Probably the earliest test was done by Cavendish in the late 1700s. And basically what he did is he took a sphere, a conducting sphere, he put a conducting shell around it, charged up the outer shell, opened it up, and saw if it had left any charge, induced any charge on the inner shell. And of course, he found that there was no charge that he could measure, and he concluded then that Gauss's law was right, that Coulomb's inverse square law was right. Well, a student of mine looked into this. He was curious, and what he discovered is that the best laboratory measurements done today are done almost exactly the same way. The only difference is they were able to use a silicon detector, a transistor, to detect that charge rather than the things that Cavendish had at hand. So he came to me, and he had this idea. He said, at the time we were building a neutral atom interferometer, and he said, well, look, yeah, this atom interferometer, right, it can measure lots of things very precisely. I bet you could do this. I mean, if the best experiment is done with a transistor, I bet we could do even better with an atom interferometer. And he was a really bright student by the name of Brian Nienhaus. He's actually doing graduate work with Debbie Jin now. And so I kind of talked to him about how you would calculate that, how we apply an electric field, our atoms get induced dipole moment, and you get an interaction which would cause a phase shift. And I sent him off to do some calculations. And he came back and said, well, you could probably do about as good as has been done today, but probably not much better. So then the natural thing that occurs to you is, well, if you can do as well as can be done just looking at stark shifts in atoms, imagine how well you could do if you had a charged particle interferometer to throw at this problem. So that's what got us going. And here's the basic idea behind this experiment we hope to be able to do with our ion interferometer someday. What you do is you imagine you have a conductor and you ground it, all right? And imagine that inside this conductor there is a cavity, and you measure the electric fields inside of that cavity. Now Gauss's law says that if I change the voltage I apply to that conductor, the fields inside that cavity shouldn't change. And if they do, you found a problem with Coulomb's inverse square law. All right? But why in the world would you expect Coulomb's law to be wrong in the first place? Right? Why would you even bother to go check it? Well, I think the best answer is because everything we know is wrong. Every time we think we've got a theory that describes something, we eventually figure out that it was really just an approximation to something more fundamental. And so if we look at Coulomb's law closely enough, we ought to be able to eventually see hints of that underlying more fundamental theory that's got to be there. All right? Another reason that you might expect Coulomb's law to be wrong is it's possible maybe that photons have rest mass. Now I encountered a massive photon once and had one of my grad students take a picture of me, but no one believes this. So we need more concrete evidence of massive photons. All right, now massive photons change electromagnetism. And the reason I think that the idea of massive photons is really important is not so much because I expect we're going to be able to actually measure the mass of a photon, but because if Coulomb's law is violated for any reason whatsoever, this is like a test theory you can apply to it. And you can use limits that you place on the mass of the photon as a way to compare different experiments that test Coulomb's law. So this is how you think about massive photons. As you recall, Yukawa's theory of exchange bosons basically says that all forces are mediated by virtual particles. The virtual particle for electromagnetism is the photon. All right, to make these virtual particles, I have to steal energy from the universe, and I can only get away with that with a short amount of time, so I can hide it all in the uncertainty relationship so the universe doesn't come and try and collect the bill, right? The amount of energy you have to steal limits the time that the virtual particle can exist, and the amount of energy you can steal that you have to steal to make your virtual particle depends on the mass of the particle you're making, right? So when you go through and calculate it, you find that the range of the Coulomb force then is going to be h bar over mc, where m is the mass of the photon, the rest mass of the photon. All right, when we do physics theories, we don't like to have large parameters, right? If the mass of the photon exists, it's at least very small. We like to expand things in terms of small parameters, right? So I'm going to define mu sub gamma to be 1 over the range of the Coulomb force. All right, and this mu sub gamma then is just proportional to the rest mass of the photon. Okay, so now, in classical electromagnetism, if I have some boundary conditions and I want to find what the fields are inside of my conductor, of course the equation I solve is Laplace's equation, right? No surprise here. And if we solve Laplace's equation assuming spherical symmetry, what do we get? We get a 1 over r potential plus a constant solution, right? This is just the point charge potential. And then this constant solution is actually really important because it's this constant solution that says I can add a potential everywhere in the universe and still have a solution to Laplace's equation. I haven't changed physics. And that's what allows me to take an electrical circuit and say, I define this pin right here to be ground, to be 0 volts, and get away with that. All right? Okay, this is all, undergraduate physics. I think we all get this. But now the question is, what happens if photons have rest mass? Well, what we have to do is we have to come up with a new equation to replace Laplace's equation. And that was done by Alexandru Proca. He came up with the Proca action, applied that to Maxwell's equations, and this is what you get instead of Laplace's equation. You get something that looks the same, it's just got this extra term here, which, of course, remember, mu sub gamma is proportional to the rest mass of the photon. Now, when you solve this equation, assuming spherical symmetry, these are the solutions you get. All right, the first solution is just a Yukawa potential. All right, it's the 1 over r potential, but then it's got this decaying exponential term, and this is what limits the range of the Coulomb force. The second solution here, the interesting thing about this one is that it's not a constant. So if photons do indeed have a little bit of rest mass, what that means is that, first of all, absolute potential has meaning. I can no longer legitimately go and just add a potential everywhere in the universe and expect the physics to remain the same. All right? If photons have rest mass, as you'd expect, light will have dispersion in vacuum. You'll get a small longitudinal component of light polarization, and fields in conductors will depend on the potential of the conductor. So that's the basic idea behind this experiment. So what we want to do, here's just kind of a cartoon diagram of what we're working on. And the idea is you would take a beam of neutral atoms, put them inside of a conducting shell, photoionize those atoms, all right, and then have those atoms diffract off of 3 gratings to form an interferometer. Then by measuring the phase of your interferometer, you can determine if that phase changes, then you know the fields inside the conducting shell are changing. So then what you do is you apply a big voltage to that conducting shell and then change that voltage and see if the fields change. And that's the basic idea behind the experiment. Okay, now, I discussed the solutions to this equation for assuming spherical symmetry. Our experiment will not have spherical symmetry, but it will almost have cylindrical symmetry. So in order to calculate how sensitive an experiment you ought to be able to do, what we did is we solved this equation in cylindrical coordinates. And what you get then are 0th order modified Bessel functions. Those are the solutions to this Proca modified Laplace's equation, assuming cylindrical symmetry. All right, and then what we did is we applied our boundary conditions, right? Inside, we're going to have a conducting cylindrical shell, all right? And at the surface, the potential will be whatever the voltage is we apply to that shell, and then, find out what happens in the middle. And then, because we know that mu sub gamma is going to be small, if not 0, we take this whole thing and we expand it to lowest order in mu sub gamma. And what we get then is this equation right here. So here's what the potential would be inside of an infinite conducting cylindrical shell, assuming that photons have rest mass. All right? And you can see in the limit as the distance from the axis of your cylinder approaches the radius of your cylinder, this just turns into the voltage you've applied at the cylinder. But inside that space, inside the cylinder, the potential increases quadratically as you move from the axis. All right? So this is the basic equation then that we can use to figure out what kind of sensitivity you might expect in this kind of an experiment. Now incidentally, this voltage right here, that's the absolute voltage that we apply to the cylinder. It's not the voltage that we read on our power supply, because our power supply is referenced to earth ground. And we don't know what voltage earth ground is, right? If photons have rest mass, we're no longer free to call Earth 0 volts. All right? And so we have to consider then that the voltage we're applying is whatever our power supply says we're applying, plus whatever voltage the Earth happens to be at. But, of course, what we're really going to be doing is not measuring this potential. We're going to be making changes. We're going to be changing this voltage and seeing if it changes. So what you do is you take a difference of 2 different situations, and then luckily Earth ground cancels out. All right? So it works out the same. So in classical electromagnetism, if I had my cylindrical shell, and I applied a voltage to it, the potential would be the same everywhere inside the shell, right? But if photons have a tiny bit of rest mass, what we get is a parabolic potential, which then meets up with the potential that we apply to the shell at the radius of the shell. So that's the equation we're working with. Okay, so how much sensitivity should you be able to get from such a device? Well, what experimental limitations do we have to deal with? All right? The apparatus has to fit inside some physical space, right? We have limitations on the length. And as you can imagine, that will make a difference. If I have a longer interferometer, my diffracting beams will separate further, right? And they'll measure bigger differences in potential as they are separated further apart. Also, the ions will interact with the potential longer. So a longer apparatus ought to give you more sensitivity, all right? Another thing which probably comes to mind if you've done experiments with interferometers, like most of you have, the velocity of the ions is going to matter. If I have slower ions, when they hit the grating, they'll diffract at a bigger angle, and they'll also, because they're traveling slower, they're going to interact with the fields longer, right? But instead of writing our equation in terms of velocity, we realized probably the smart thing to do is to think in terms of the kinetic energy of the ions, because well, what really limits how slowly you can put your ions through the apparatus? Well, the thing that limits you are stray fields. If your ions are moving too slowly, any stray fields are going to bounce them around and have their way with them. And so kind of, instead of thinking in terms of velocity, we think in terms of kinetic energy. And we think of that kinetic energy in terms of a potential, a voltage, the voltage it would take to bring our ions to a stop. And then what we can do is we can say, well, look, if I know I can control the stray fields at some level, we just have to make sure that our ions have a voltage that is much higher than the stray voltages, the stray potentials inside the apparatus. All right, the grating period, of course, matters. Smaller grating period means bigger diffraction. The radius of the apparatus is another important parameter, because remember, the non-classical field is quadratic. If you run your ion beam right down the center of your tube, you're not going to get a lot of sensitivity. If you can move it off to the side where the non-classical field should be bigger, you're going to get more sensitivity. And the bigger you can make your apparatus, the further out you can move your ions. All right, and of course, if you can apply a bigger voltage change, you'll make a bigger non-classical field. The mass of the particle is usually a big deal when you do matter wave interferometry. But it turns out for this particular application, the mass of the particle hardly matters at all. All right, that gives us a lot of freedom. So, with that in mind, you go through and you do a bunch of calculations, and here's the sensitivity you get. And it's just what you expect. It goes as 1 over the length. A longer apparatus will mean I can detect a smaller photon rest mass. A bigger applied voltage means I can detect a smaller photon rest mass. Smaller grating period means smaller photon rest mass. This parameter here, A, is basically the distance from the furthest out arm of our interferometer to the center of symmetry of our cylinder. And as you see, if we move further out, we can get more sensitivity and detect smaller photon rest mass. V sub s is the voltage it would take to stop our ions. So that's related to the ion's kinetic energy. And then delta phi is the smallest phase shift you ought to depend, which depends on statistics, right? How many ions you can detect to build up your signal before things drift. All right. Now you notice that the mass of the ion does not show up anywhere in this equation. Well, actually it does. There's this parameter Q here, which looks like this. And the thing you should know about Q, don't think too hard about it, just know that for any reasonable set of experimental parameters, for any ion, any mass of ion, it's smaller than 1. All right? So pretty much you can ignore it. If you deal with electrons, things get a little hairy, though. So luckily we're not dealing with electrons. All right? And then notice the square root right here. The square root means that if I double the voltage I apply, I only improve things by √2, right? On the other hand, if we can't actually realize the setup that we wanted to, we only lose by √2, all right? Okay, so what we did to calculate kind of an expected sensitivity you could get from this device is we threw in some reasonable experimental parameters, right? A spacing between gratings of 1 meter. We wanted to have our ion beam 25 centimeters away from the center of the cylindrical conductor. Gradient spacing of 200 nanometers, applying a voltage on the order of 400 kilovolts, and assuming that we can get stray voltages, stray potentials inside the conductor in the presence of the ions down to below the millivolt level. All right, when we plug these numbers into that equation, what we find is we ought to be able to detect a photon rest mass on the order of 9 times 10 to the minus 50. That's pretty small. All right. Not only is it small, it's a huge improvement over what's been done so far. It turns out over the last 2.5 years, laboratory measurements, laboratory limitations on photon rest mass have only gone down by a factor of 2.5 over the last 38 years. This, however, would represent a factor of 100 improvement. So it'd be a big leap from where things have been done before. Now I should point out astronomers can put a much smaller limit on the photon rest mass than this. But there's two problems with the astronomical measurements. First of all, they do involve models. So there's a possibility that there's a mistake there. But the real issue I have with astronomy is they're actually measuring photon rest mass. What we're really doing is looking for violations of Coulomb's law and parameterize it in terms of photon rest mass. So I don't lose too much sleep over astronomers meddling with my experiments. Now, another way that violations of Coulomb's law, inverse square law, are parameterized is by assuming that the potential of a point charge doesn't go as 1 over r, but it's 1 over r to the 1 plus delta. All right, and this is the more traditional and more commonly used way to parameterize deviations from Coulomb's inverse square law. And if we were to parameterize things that way, our expectations would be that the experiment would actually do better by a factor of 10 to the 5th. That actually makes our experiment look a lot better, but we like to think instead in terms of photon rest mass because when you think about it, there's some weird problems here. That when they do this, they're assuming things like that I can just add together the electric field from a bunch of point particles, but assuming that the point particles are arranged the same way they would be if classical electromagnetism was correct. There's a bunch of weird problems with doing things this way. So I'm mostly going to talk about parameterizing with photon rest mass. Okay, as you might expect, we're not really going to use an infinite cylindrical conductor to perform the experiment. And so what we did is we did our calculations assuming an infinite cylinder, and then we did some numerical calculations to see how the classical and non-classical fields in a finite conductor with holes in it for laser beams and ions to come in and such would compare to an infinite cylindrical conductor. And so these are some of the calculations. We did a calculation of the classical fringing fields to make sure that fields leaking in through the holes in the conductors wouldn't cause problems. And it looks like they're going to be extremely small and not a problem at all. And then we calculated the non-classical potential. And what we see is that in the region where the interference will be taking place, it pretty much mimics the field you would have for an infinite cylindrical conductor. So things look good. All right. Now at this point in my presentations, usually people have a few questions for me. All right. One question that they always have is, are you about done talking? And the answer is not even close, and it doesn't get any more interesting. All right. But another question that people have is, if the mass doesn't matter, what ion do you use? Well, we're planning on using strontium. So why strontium? What's great about strontium? So let me tell you a little bit about strontium. All right. First of all, like I said, the mass doesn't really matter. We can use any ion, and it really won't affect the sensitivity for this experiment very much. All right, so that gives us some freedom. But one thing that does affect the experiment is the period of the grating. All right, and so we thought it would be kind of cool if we could use, if you use an infrared laser or a red diode laser, you get pretty small grating period. But it would be cool if we could use the 4 or 5 nanometer ultraviolet diodes that are available, right? It's not a hard technology to work with, like maybe trying to work with a dye laser or an excimer laser, but it's still a relatively short wavelength compared to other diode lasers. So we thought, let's look into this. And so what we did is we searched the Crookes atomic line database for ions that had a strong transition out of the ground state near 4 or 5 nanometers. And this is the list you get. And what you see are 3 elements that maybe you might not want to try to laser cool. It might be a little bit of unknown territory. And then there's strontium. And we were really happy when we saw this because strontium has some other great properties. First of all, neutral strontium has been laser cooled extensively. It's been extensively studied, mainly in the clock community, also for other experiments. But even more importantly, the level structure and the actual wavelengths in the level structure are almost identical to calcium, which we already laser cool at BYU. So it's not new technology to us. Another really cool thing about strontium is that it is easily photoionized. Normally when you go to photoionize something, what you think is, I've got this atom here in the ground state, somehow I've got to drive it to the continuum, and it's going to take a bunch of laser power because whatever the wavelength of my laser is, I'm not going to have very good overlap with the continuum, right? I've got these states spread all over the place. But it turns out that strontium has an autoionizing bound state. It's a resonant bound state, but which ionizes in about a nanosecond. That lives just barely inside the continuum. And it turns out we can get to that state by using one of the photons from our cooling laser plus a photon at 4 or 5 nanometers. How convenient is that? Right? If it had been 420 nanometers, this would have been harder, or 350. So we thought this is a nice coincidence. It looks like nature wants this experiment to be done. And so we pushed forward, and then we realized strontium has another nice feature. There is a relatively abundant isotope of strontium, strontium-87, that has hyperfine structure. Now, hyperfine structure is great because that means instead of using like a Bragg grating for my optical gratings, I can use a Raman grating. In a Bragg grating, it's just a standing wave, right? And I get multiple diffraction orders. But if I use a Raman grating, I've only got 2 states. My interferometer only has 2 arms. So instead of having lots of different arms going in different directions, I only have 2 arms in my interferometer. That makes analysis a lot easier. Furthermore, the output of the interferometer won't just be interference fringes in space. It'll also be an interference in the internal state of the ion. So depending on the phase of the interferometer, you'll get more or less ions coming out in one hyperfine ground state versus the other. So you can detect the output of your interferometer just by shining a laser on it, which is resonant with one of the hyperfine ground states, and seeing how much light you get. So here's kind of a diagram of how it's all going to come together. We start with a lump of strontium. We heat it up in an oven and get a beam of strontium shooting into a little vacuum chamber. Then we have lasers that come from all directions, and we laser cool and trap the strontium in a magneto-optical trap. Now, this isn't going to be any magneto-optical trap. It's going to be in an Elvis configuration. That stands for low velocity intense source. And this is a technology which was developed in Boulder, Colorado. And the basic idea is this. I have lasers coming from all directions. I have a laser coming from this direction, and it's retroreflected by a mirror, all right, to help make my trap. But if I put a little hole in that mirror, there will be a shadow in the retroreflected beam. So in the very center of your magneto-optical trap, light forces will not be balanced, and atoms will get pushed out and fly through that hole in the mirror. Then you've got a cold beam of atoms flying through your apparatus. All right, so our cold beam comes in. Then we will photoionize the atoms to make ions, and then we can apply a potential right here so that after they're photoionized, they can get accelerated to whatever velocity we want. The ions come through. They interact with 3 laser beams, which are overlapped with 3 other laser beams at a slightly different wavelength to drive stimulated Raman transitions. And that splits and recombines our ions quantum wave. And then we detect the phase of the interferometer by sending in another laser, which is resonant with one of the hyperfine ground states and measuring fluorescence. All right, so here's the apparatus. I showed you kind of the schematic version of the apparatus. Now I'm going to show you a more realistic version of the apparatus. This is a real video of what this really looks like. All right, are you ready for this? I just have to pull up the file here. Here we go. So this is what really the experiment really looks like, right? So we go inside here, we've got strontium atoms, they're laser cooled, they come in here, they lose an electron, and then they interact with 3 ultraviolet laser beams, which splits and recombines the quantum wave, and then we look at the interference. Anyway, it's just a cute little video that we put together our college wanted to show off some of the research going on to the wealthy donors and prospective students. So they bust in some high school students and brought in the wealthy donors, and they wanted us to have something pretty to show them. So since silly videos seem to be popular today, here's another silly one for you. All right. Okay, but back to the presentation now. Let me just show you, hit the wrong button, some of the parts of the apparatus that we're putting together. So we recently finished constructing the laser that will do the laser cooling. It's basically over here. I don't know if you can see this. There is a little Thorlabs laser head. We have a diode in there, a 922 nanometer diode, and a grating. We use feedback to stabilize the diode. So a little external cavity diode laser. That light runs through a couple of isolators and then is amplified by a tapered amplifier. All right, this is the tapered amplifier running. It turns out that 922 nanometers looks pink on our camera. And then this 922 nanometer light then goes into a doubling cavity where we double pink to make blue. It's not really pink, it's infrared. And then this is the light which we will use to laser cool the atoms and make our cold source. Now, I just have some electronic instrumentation here just to point out we've developed a lot of electronics that are much quieter than and wider bandwidth than some of the things you can get commercially. If anybody works with lasers and wants to know about our ultra-stable laser current drivers or PID controllers or our digital controllers, come talk to me. My grad student who developed most of this will actually be doing a poster later today. He's right here. And he can tell you all about things. We'll share you our circuit boards, and you can toast your circuits right away and have some pretty decent electronics to make your lasers happy. All right, here's the vacuum chamber. We have not cooled atoms yet, but we're pretty close. We've got our laser working. We've got the vacuum chamber together. Here's the mirror I mentioned that has a little hole in it so that it casts a shadow in the light so that the atoms get pushed then through the hole. We are right now characterizing, making sure that we didn't damage the surface and make it wavy or non-reflective when we drilled the hole in it. And then that will pop right in here, and then we'll be able to run our apparatus. This is the oven where we heat the strontium up. These coils, so inside here are the magnets for our magneto-optical trap, and these coils right here tweak the magnetic field just a little bit so that we can slow the atoms as they enter the magneto-optical trap. Now, the magnets that we use here are actually permanent magnets rather than electromagnets. They're rare earth magnets. And that has the advantage that I don't have to keep a power supply running. I can't turn my mott on and off, but it's very stable. It also has another side effect, which is kind of nice, or kind of horrible, depending on what you're trying to do with your mott. All right? But when you have permanent magnets, you can actually model a ring-shaped permanent magnet as an electromagnet on the inside with current, an electromagnet on the outside going in the opposite way. So what happens is you get a field, the kind of field you need for a magneto-optical trap, so this is just showing one quadrant, and here's where my atom trap is over here. All right? And as I move in any direction, the magnetic field increases, and that's what you need for a magneto-optical trap. But notice, along the direction that the atoms are going to be pushed, the field increases, then it goes back to zero, and then increases in the opposite way. And that does an interesting thing as the atoms come out of the trap. Because what happens is, as the atoms come out of the trap and they get pushed by the light, you can see here's the magnetic field. The blue line is the magnetic field along this direction as we leave the trap. All right? So what happens is the atoms come out of the trap, they get pushed by the laser beam, and very quickly they get Doppler shifted out of resonance and they don't get pushed anymore. So they come to kind of a slow velocity. And you see that right here. So in a traditional low velocity intense source, your atoms would get pushed a little bit, then they'd get out of resonance, and they'd come out with a very low velocity. But because the field actually turns around and gets pretty big when we use these permanent magnets, we calculated that the atoms are going to get pushed, and then they're going to get pushed again. It's essentially an inverse Zeeman slower. So our atoms are actually going to be coming out of there at almost 150 meters per second. Now that may seem like a dumb thing to do. We went to all this trouble to make slow atoms, right? Well, it turns out 150 meters per second is not that fast. It's just a little bit faster than what I mentioned we wanted to have in order to achieve our best sensitivity for photon rest mass. All right? The nice thing about having them go a little bit faster, though, is then they don't sink under gravity as much. So by the time we get out, we're ready to ionize the atoms. If not for that, the atoms would have fallen considerably, and we'd have trouble aligning everything. Whereas here, they're moving just fast enough that we don't have to worry much about gravity, but slow enough that it won't really affect our sensitivity. So anyway, this picture right here has no scientific merit, but I thought it was really pretty. All right, this is a picture. Oh, there's one person who's still awake. All right. This is a picture of a vapor cell. It's a pretty common thing to see in an experimental laser lab. It's just a place where we heat up some strontium and we send lasers through and look for absorption. The thing we're going to try and do here that's a little bit unique is that in this experiment, in addition to having a laser which is tuned to the cooling transition, right, that drives the atoms out of the ground state into an excited state, we also have two other transitions that we have to drive. Well, actually three. We have the laser that does the ionizing, and then we have the two lasers that drive the Raman transitions. And neither of them make transitions out of the ground state, right? So if I have a bunch of strontium in the ground state and I shine my Raman lasers in there, there are no atoms, there are no ions there for them to interact with, and we won't get an absorption signal. So the normal thing to do would be to get something like a discharge cell where you had lots of atoms in different states and ions in different states. But it turned out that the people who make these, we called around and no one wanted to make one for strontium that they would guarantee would last any amount of time, because the strontium just likes to absorb to things. So well, what we're going to do instead is we're going to take, first lock our cooling laser to the ground state transition. Then once we have the cooling laser, we'll shine that plus the ionization laser. It turns out we don't have to lock the ionization laser because the transition's a nanometer wide. Overlap those two, all of a sudden what we'll have is we'll have a column of ions. And then we can lock our Raman lasers to that. So that's how we're planning on locking our lasers. All right, so where do we go from here? So we're very close to having slow ions. We've got the cooling laser. We've almost got it locked. We've got the ionization laser, which we don't have to lock. So very soon we should have a slow ion beam. We've got the interaction chamber. Our machinist has parts for that. I'm working on the electrodes, which will accelerate the ions. And if anyone has expertise at accelerating charged particles, I've been doing simulations and trying to figure out how to accelerate them this way without making them blossom out the other way. And I would love to hear what anyone had to say on that. And then we've put together the lasers for our Raman transitions, but they're going to be pretty tricky trying to get two lasers locked precisely, the 5 gigahertz hyperfine splitting from each other. And so that's going to take some doing to get that all tuned up. But then once we have it all together, we can do some cool experiments. All right, I want to thank my students who work with me. These are my 3 grad students right here. Chris Erickson is the one who's done the most work on this project. He's my PhD student, and he's actually here. He'll be giving a poster. He actually worked on a different experiment for me for most of his PhD. And at the time, he was my only graduate student, and I got grant money to start working on this experiment. I didn't have a grad student to work on it. I was trying to do it all myself, and I wasn't getting very far. So finally, after telling him many, many times, I don't want you working on this experiment because that would just be horrible to change your thesis right in the middle. After telling him that for a year, I finally decided I really needed his help. And so he's been working the last year and a half. And the fact that we have some things built is because of him. I've also got 2 master students, and these are a few of my undergraduates. We have a few more. These are the ones that happened to be there when we remembered to get a camera to take a picture. And also, yeah, so here's more of our undergraduate students, some recent students who've graduated. Brian Nienhaus is the one who came to me with the great idea after doing the GRE practice exam. And I'd also like to thank Scott Bergeson, and especially Mark Kasovich. I did a postdoc for him, and honestly, the ion interferometer we're building is a whole heck of a lot like the cesium interferometer I worked on with him. I really learned from him the right way to do this, why Raman transitions are really the way to go, and such. And thank our funding agencies. How am I doing? Did I come in short?
8 minutes left.
Oh, that means I'm going to get grilled, doesn't it? That wasn't very smart of me.